I'm Nick.
And I'm Cooper.
And we did question number 8 for the physics video project, which reads, the PV diagram below shows the 3 steps in a 3-cycle heat engine. The gas has a CV of 2.5 R and a CP of 3.5 R. The steps are an isochoric heating, an isothermal expansion at 800 degrees Kelvin, and an isobaric contraction with a pressure of 75 kilopascals. For each step in the cycle, determine the change in thermal energy, the heat transfer, and the work. In addition, determine the thermal efficiency of the heat engine.
We know that at point B, the temperature is 800 degrees Kelvin because it is stated in the question. We can use this temperature to solve for N using PV equals nRT. But first, we must convert the pressure and volume into the appropriate units, meters cubed and pascals. We use the 800 degrees Kelvin to obtain N equals 0.009 moles.
In order to continue on with this problem and calculate the temperature at point A in order to solve for the other remaining variables such as the thermal energy and the heat transfer and the work. So again, we use PV equals nRT in plugging in the moles that we calculated in step 1 to get the temperature at point A to be 200 degrees Kelvin.
Step 3 is to determine the delta E thermal work and Q from A to B. This is an isochoric process, meaning there is no change in volume, so the work equals 0. We also know that Q equals NCV delta T, CV being used when the volume is constant. This provides that Q equals 113 joules. We know delta E thermal equals Q plus W, or 113 joules, the same as the Q.
The next step in the problem is to determine the temperature at point C. However, because the process from B to C is an isothermal heating, that we know the temperature is equal to 800 degrees Kelvin, indicated here and proven through the equation, PV equals nRT.
Step 5 is to determine Q, W, and E thermal from B to C. We know that work is equal to this integral here, where P of V is a function for pressure in terms of volume. This function can be written as P of V equals N naught R times T naught over volume, where N naught and T naught are constants. Integrating this function of P of V, we obtain that W equals negative N naught R T naught ln V final over V initial. We use this equation here and input the final volume and initial volume to obtain a work value, negative 83.2 joules. Then using NCV delta T equals delta E thermal, we derive that delta E thermal equals 0 joules. It is 0 joules because here we see that the final temperature and initial temperature are the same, multiplying the entire equation by 0, yielding delta E thermal equals 0. We then use Q equals negative W plus delta E thermal to solve for Q, obtaining Q equals 83.25 joules. This makes sense because it's equal to and opposite to the work, and the delta E thermal equals 0.
Lastly, we can solve for the change in thermal energy, the heat transfer, and the work for the process from C to A, which is an isobaric contraction with a constant pressure of 75 kilopascals. So using the equation for the change in thermal energy, the N times the CV times the delta T, we can get that the change in thermal energy equal to negative 113 joules. Because it is a constant pressure system, we can say that Q is equal to N times the CP because of the constant pressure system times the change in temperature. Therefore, plugging in all the appropriate values, we get that the Q is equal to negative 158 joules. Then, using the relationship between Q and W and the change in thermal energy, we get that the work is equal to the change in thermal energy minus the heat transfer. And then plugging in the values, we get that the work is equal to 45 joules.
The final step is to solve for thermal efficiency. Thermal efficiency is calculated by the net output of work over the net input of heat. The net output of work is simply the sum of all the works. The net input of heat is simply the sum of all the heat inputs. Using the obtained values, we input them into the equation for thermal efficiency and obtained a value of 19%.